Okay, so we're talking of the catalysts being used for the addition reaction of our alkynes. There are two kinds of catalysts for the hydrogenation of alkynes. The first one is the use of a heterogeneous catalyst. Now we have the P2 catalyst, or commonly known as the P2 catalyst, or also called as nickel boride. And we have the Ringler catalyst. We'll use this one, we'll use palladium in the presence of calcium carbonate. You'll get a Syn addition, which means that the hydrogen is added on the same side. And in such a way, you will actually obtain a cis-Alkene or a Z-Alkene. So another possibility for the addition of your alkynes in the presence of hydrogen is the anti-addition of hydrogen. To proceed to the trans-Alkene from your alkyne, we used lithium or sodium metal in ammonia or ethylamine. So lithium in ethylamine, like this one, ethylamine, or sodium in ethylamine at a very low temperature. We follow this route. Actually, what we produce is an we would proceed with anti-addition, which means that the product that we obtain is a trans-Alkene. So the mechanism that involves in this one, in the mechanism for this kind of reaction proceeds actually with the involvement of radicals, and we'll discuss that in the next chapter. For now, just know that using this kind of agents, you have your hydrogen, and you have your lithium, and you have your ethylamine. At a very low temperature, you actually obtain our alkynes here. And, okay, so the first step actually for using this one is the use of a lithium atom with that, where it donates an electron to the pi bond of the alkyne. Okay, once you get your electron, donates an electron atom, what will happen is that one of the carbon, okay, always know that a bond is composed of 2 electrons. You still have time, right? So what will happen is, so one bond is composed of 2 electrons. So if it pairs up with lithium here, okay, if it donates an electron here, it will happen one of the carbon will have 2 electrons and the other will have 1. And once you produce this one, you actually, so one of the bonds is composed of 2 electrons, will pair up with 1 electron here to form dot dot, and the other will be unpaired, it will have dot. And what you get actually is a radical anion. In the presence of ethylamine, so the carbonide anion, the carbon with having an electron, will abstract the proton from ethylamine, and what you'll get actually is a carbon double bond C hydrogen here with a dot. Once you produce this vinylic radical, vinylic, since you have your C double bond C and a dot. Okay, once we have a dot, we call that one as a radical. An unpaired electron, we call that one as a radical. Whenever you have an unpaired electron, we call that one as a radical. So this, once you produce your vinylic radical, what will happen is that your lithium, again with an electron, will donate its 1 electron to your vinylic radical to produce your dot dot, 2 electron carbon. It is negatively charged, and it will abstract at the proton again with your ethyl amide, and of course the electrons from your hydrogen nitrogen will go to your ethylamine to form your ethyl amide. Okay, so what will happen is once it abstracts, you get your alkene here in a trans configuration. So the anion acts as a base, this one, and removes the proton from the ethylamine. And what you will get actually is an ethyl amide, as one of the side products. Okay, so that is how the anti-addition of your alkyne proceeds if you use sorry, if we use lithium and ethyl amide as our agent, and then we can further, since you get your amide, ethyl amide can actually acidify that one with ammonium chloride to recover back your ethyl amide. Since once you get your proton here, you actually get your ethyl amide, so we can acidify that to recover this one. That's why there is a second step here, just in case you want. Basically, in the step 2, you already recover your trans-Alkene. So that's the anti-addition. So problem, write the structure of compound A used in the synthesis of the perfume to have the jasmine here. So you have your palladium calcium carbonate. This is a Lindlar catalase, and of course this is a Syn addition. So this is where it adds here. Of course, it starts, use this Lindlar catalase, and you have your double bond here. It most probably starts with a triple bond here, and you have using this one for this. It's a very simple one. How would you convert 2-9 into E2-9? So E, this one is E. What's that? So the trans or cis? Anyone?
Trans.
Okay, it's a trans. So if since it's a trans, it follows the anti-addition. So you will have to use your lithium in the presence of ethyl amide. Now that will be your reagent. Very simple. So far what you have learned is the hydrogenation, is the somehow, no, if you have, for example, this kind of problem, you'll be asked what will be your starting material. If you have starting material to your product, what will be your agency. So we are actually now on the organic synthesis. So we have already an introduction to what we call as an organic synthesis. So you have learned quite a few tools that are useful for organic synthesis. You have learned the nucleophilic substitution, even for you have your alkyne, you can proceed with nucleophilic substitution, and you can also proceed with elimination reaction. So far in all that we have discussed the chapters, we also have the hydrogenation reactions. So now we'll consider the logic of organic synthesis and the important process of retrosynthetic analysis. Then we will apply nucleophilic substitution. Okay, we'll use nucleophilic substitution and hydrogenation reactions to the synthesis of some simple target molecules. It's very important. Why do we do organic synthesis? So it's a process simply of building organic molecules from a simpler precursor, and that's what actually chemists are good at. But you have to remember that even chemistry, it's a very complex. It's a very wide discipline. It have different aspects of chemistry, but one aspect is the organic chemistry. In organic chemistry usually involves the organic synthesis. Synthesis of organic compounds are carried out for many reasons. We develop new drugs, carry out organic synthesis in order to discover new molecules with structural attributes, for example, that will have medicinal effects and reduce undesirable side effects. So here is the structure of a drug. It's an HIV protease inhibitor. So it's an anti-HIV drug. So this one is designed in the laboratory. So it started as a research, small scale synthesis in the lab, and then it's being expanded to a large scale synthesis where it can be produced in companies and manufacturers to be used as a drug. So that's what chemists are. We usually synthesize drug. Another example of synthesis of drugs and vitamins, we have the vitamin B12. It was synthesized in 1972. Usually the synthesis of vitamin B12 took 11 years, required more than 90 steps, and involved the work of nearly 100 people. So from then on, actually, there are chemists were able to improvise the steps with the mechanisms involved on how to simplify the steps so that the processing or the synthesis of most organic compounds will be simplified and also cost effective. So imagine years ago, it took how many steps? 90 steps. Imagine just a one-step reaction, no? Complex naman ganit. You have 90 steps. Imagine it's very, very tedious. And look at the structure of this vitamin B12. Yes, it's very complex. But now we are taking vitamin B12. Personally, I take vitamin B12 that is synthesized in the lab. Of course, you can take the natural vitamin B12, but it can also be synthesized in the lab. So the organic synthesis typically involves two types of transformations. We've learned that we can convert functional groups from one to another. We've learned that in nucleophilic substitutions, right? You can easily convert one functional groups to the other, and you can create new carbon-carbon bonds. Let's say, for example, you have your alkanide and you have your alkylylide, right? Earlier in the examples, you create new carbon-carbon bonds. You can extend the number of carbons. So there is a way of what we call as a retrosynthetic analysis. We plan an organic synthesis, and sometimes it's possible to visualize from the start all the steps necessary to synthesize a desired target molecule from previous precursors. Now, previous precursors, what are our starting materials? In this case, we know where we want to finish, what is our target, and where we start. Now, earlier, I have mentioned that if we are asked what your finished product is, your product, you have to know the structure, and you have to know your starting structure of your material. So the structure is very, very important. You really have to draw if you want to get your product. Okay, so I will just finish this. It will be the end of chapter 7. Okay, so when we say retrosynthesis, now we have to, if this is our target molecule, no, we have to know our immediate precursor, earlier precursor, and the next precursor, and then you have your starting compound. So if this is our target molecule, baliktad ka, retrosynthetic. This is your target molecule, you will have to know what is the next precursor, then what is the precursor before that, and what is the precursor before this. And then you can have your starting compound from the smaller one. Okay, this is the retrosynthetic way of preparing your organic compound. So sometimes in doing retrosynthetic analysis is necessary to generate as many possible precursors and hence different synthetic routes. So for example, you have your target molecule, then you can have plan A, plan B, plan C, no? And then you have your first precursor, and then you have to think what will be your second precursor, if there's another precursor, and would it be a good starting material? So there's actually different pathways. For example, earlier, no, we were asked to choose how to prepare. We are given a different reagent, starting materials. Will it be possible if you use the first two, or be possible or the other? No? So you have to discuss within yourself, no, would it be possible or not to have that? If not, so you have to discuss on the advantages, disadvantages. You have to discuss what are the pros and cons. You have to do that. And then later, actually, when you really have to manufacture that one, you also have to consider on the cost-effective process. And another way to consider the length, the time to prepare your target molecule, and how many steps will be involved. Those are the things that will be considered when, soon if you really have to proceed with synthesis. So you have to identify your precursor, and one very important aspect of retrosynthetic analysis being to identify those atoms in the target molecules that could have complementary opposite charges. Okay, so for example, you have this one, the alkyne ions. You start with this material, and this is your this is your target molecule, right? It's your target molecule, so you have to consider what will be your precursor. If this is your target molecules, you start with this alkyne and ion, and then you have here before this one, what is the starting material before this? So you have this. So this is the retrosynthetic process. The normal synthesis, you have your starting material. Okay, you have this, and then you have your amide that will obstruct your proton. Then so you have your alkynide here. Then you will need to have another agent, no, to be attacked by your alkynide. Like you have your alkyl halide here, and this it can attack to produce this one. So this is the normal synthesis. But the retrosynthetic analysis is if this is your target, this is the product that you desire. Before you obtain this one, unsa pa may imuhang precursor ani. So you can think, oh, you have your alkyne here. Then if you have your alkynide, actually it can act as a nucleophile. So you have this. But before you produce your alkynide, asa niya siya gikan? So you have your alkyne as your starting material. Okay, and if you have already known this is your starting materials, you have retrosynthetic analysis, so you can use this one. You have this na synthesis, and then what is their agent that will be needed to produce this? So you have your amide. So once you have your alkynide, then unsa pa iyang gamit, no, to produce your product. Of course, you need another material so that it can act as a nucleophile para madungagan iyang carbon. So notice here, this is your material and this is your product. You need this portion here. So what will be your another agent to have this? So you need an alkyl bromide here, or alkyl halide. So any alkyl halide. Okay. So this is the retrosynthetic analysis of synthesis, and you will encounter more of this in the next chapters and even in this chapter. So helpful hint, you need to solve problems, no? End of chapter problems called synthesizing the materials will give you the practice to retrosynthetic planning. So there's always have to practice end of chapter problems. Okay, so that ends our discussion for chapter 7 in summary. There's this method of summary of methods for the preparations of alkenes and alkynes. Number 1 is the dehydrohalogenation reaction. You have your HX, your halogen. You eliminate this one to produce your alkene. Now, these are the examples. Second is your alcohol. You eliminate the HOH to produce your alkene. Okay. And then you have your alkyne. You can prepare your alkene, no, based from your halogen halides, alkyl halides rather. From your alcohols, you can also prepare your alkene, but you can also prepare your alkene from alkyne. Okay, and you can have your alkene to be on cis, same side, or trans, or in the E configuration, depending on the catalyst that you use. Okay, so we have already so far discussed on how to prepare alkenes and alkynes. Okay, so that ends our lecture for chapter 7 already. And I will give you a problem set where you can practice now. But first, I think you have an assignment or a problem set to finish. And I will upload another problem set that you can work on. Okay, please do not forget to due date na di ay. There are people who didn't submit problem set number. It's number 1, 15, is number 2 is completed. And problem set number 1 ay isa wala 1 and 2, 3. Na isa wala nag-submit. So problem set number 3 na ay tulo wala nag-submit. For those katong late, you can actually submit, but of course there is a deduction. I really encourage you to submit even if it's late. No, there is a deduction, but please submit. Okay, so that ends our session. I will have to give also minimum of 3 problem at most, 3 problem sets now for chapter 7. So this one is from chapter 6. So I'll give you problems that will be chapter 7, and then we'll have our quiz. And next meeting will be starting on chapter 8 now. So do not forget to indicate your attendance for today. I have uploaded the lecture discussion already, but I don't know why it still didn't appear. But I'll check it later. Okay, so that ends our discussion for today. I'll see you next meeting. Do you have questions?
No quick question.
Yes.
Um,
Si Ayan.
for clarification lang, na-discuss na to ang neighboring group participation.
Neighboring group participation. Nasa man na?
I think, appeal ko po siya sa mechanism. Kung naman ko siya sa problem set mo, I think nasa problem number 3 ang neighboring group participation.
So unsay mong pangutana ayan?
Ang mechanism sa neighboring parties. Neighboring parties.
Unsa lagi nga problem?
Kanang 6.49.
This
Na-confusion
one.
ko sa yes, na confusion sa yung mechanism. Although naka-answer man based sa YouTube, pero I think proper explanation. Medyo na
When S-bromopropanoic acid reacts with concentrated sodium hydroxide, the product from after the acidulation is this is, of course, the normal stereochemical result for an acidic reaction. So, however, when the same reaction is carried out to the low concentration of hydroxide ion, takes place, the retention configuration produce S2 hydropropanoic acid. The mechanism is neighboring group participation, retention and configuration. So it will assist, no? Actually, this one, your AG, no, acts as also as a Lewis acid. So we will discuss this later. We'll try to solve not on our time. If you want, we will devote to the reaction to the problem solving for the problem sets, no, just to see. But this mechanism involves neighboring group participation. The neighboring group participation simply have to indicate, no, what the groups, the group of atoms, no, that is involved when you do the reactions. So here you will actually propose a mechanism. No, this is more challenging actually, the 6.49, 6.50. Some of this actually, this one we haven't discussed, but you will have to propose, and this is the basis actually why I give this problem. You will propose on the kind of mechanism. The basic one actually is you have the SN2 and the SN1 reaction, no? Or you have the SN2 reaction here. But then, since you have your Ag plus acting as an acid, no, and it takes place via the overall retention of configuration. So that's why you have to propose why you will have to have an S retention of configuration and not the R. So this is the case 6.49, 650. Actually, you have to propose, you have to compare and contrast, no, which mechanism will have to be used. And the neighboring group participation, simply have to use the species in the group of atoms that will be involved now when you use your Ag as a Lewis acid. So it actually also acts like a catalyst, like the same way that we had our earlier gamit ganina. Yung catalyst na to ganina. So we'll discuss this 6.49. This one is the more difficult. That's the reason that I have included this one in the problem set, no? Because for you to be challenged more on how you will answer. So we'll discuss this 649.50 and also for the others, but not in our lesson or atong lecture time, probably in our lab time when we have our time. Tomorrow you will have a simulation activity, another activity that you can start. And if you have time, probably I can just record on that, or we'll set on a time to you have clarifications for your problem sets. Okay. This one actually is a higher level mechanistic approach, 49 and 50. This is not the usual SN2 for SN1 reaction. So we'll discuss that next meeting. Okay, what else? So it's already 6:25. So can send me a message if you still have questions, and we'll continue next meeting. And just watch for the another problem set that I will upload. Okay. So that ends our lesson. See you next meeting.
Thank you, ma'am.